Okay, so the next thing I'm going to talk about is design and control. Um, so, in general, there are two types of designs that we use in psychology. One is called within participants, and that's one where we test the same person multiple times. And the other is between participants, and that's where we test people only once, and there's like multiple groups of different people. And uh, Why do we do this? Well, when you learn next week about statistics, there are different statistics that apply to these. When we do a t-test or an ANOVA, you're going to see independent samples and correlated samples in the program that we use. And when it's within participants, it's correlated samples, and when it's between participants, it's independent samples. And we do this because there are certain things that are best tested where a person serves as their own control. Um, but then there are other things that it's better to test different groups of people because you can't test people multiple times. In the last lecture, I used the example of the Milgram experiment. You can't run that experiment multiple times on the same person because once they've been in the experiment, they already know what your game is. And so they're not going to behave in a way that, you know, that can be tested twice. Um, so that's the big difference between these two types of designs. So here's an example. We have five participants, and we give them a control test. Let's see that it's, you know, their blood pressure or heart rate at rest. So you come into a doctor's office, and I take your blood pressure, and I see what it is. And then I put the person on a treadmill, and they have to run for 15 minutes. And I measure their blood pressure after that 15 minutes, and I see whether or not it changes. That would be an example of a within participant design because I have you in a control condition where your heart's at what it's normally at, and I have it at a test condition where your heart's beating after being under stress. And so for participant one, let's say that whatever it is that I'm measuring, it's at first it's a two, then it's a seven. For participant two, I measure them at rest, it's four, and after exercise, it's at eight. Experiment participant three, they at rest are at three, and then an experimenter at 10. Person four, they must be healthy because their blood pressure doesn't change at all. It stays the same. And then participant five, where it goes from seven to eight, it doesn't change all that much. So that's a within participant design. You test the same person multiple times. Now, some of the problems within participant design is something, one is called regression to the mean, is that often when you take a measure of someone on something, the second time they take it, people that did really poorly tend to do a little bit better. People who start off doing really well tend to do not so well. That's because the person who did really poorly, it's not just that they were bad at something, but they were unlucky. And so they did really bad. And those that did really well, not only were they good at it, but they also were a little bit lucky. So that's an issue. But the other one has to do with the social science equivalent of what's called Heisenberg's uncertainty principle. If you ever watched Breaking Bad, the character, Walter White is named Heisenberg. This is the same Heisenberg. And the idea is that for Heisenberg is that you can't know in subatomic, particles where an electron is or what its voltage is at the same time because, you can know one or the other, but not both. The same thing here. Once you test someone, testing them again on the same measure will bias their response the second time they take it. The Milgram experiment is a good example, but in any survey where you ask someone, to answer 10 questions about their views on the environment, they'll remember if they did it a week ago, what they answered a week ago. So this is a problem with within participant designs. Um, so within participant designs are best used when you're not using the same exact test twice. And for more advanced designs, there's something called a yoked ordering, but we don't need to worry about that too much right now. But that's where you start half of your participants with a within subject design, and you do the order in two different ways. So in the example that I gave last with the blood pressure, you might not measure what their resting heart rate is at first. You might actually have them come into the laboratory and have them run 15 minutes, measure them then have them rest for an hour, then measure their heart rate afterwards. The other half, you would have them, you measure their heart rate and then have them do the running test. Um, but that's what we mean by yoked order. Now, between participant designs, what we have is we have a group that we identify as the control group. So these are people that we don't have run at all. So participant one, we measure their heart rate when they come to the lab at two. Participant two is a five, participant three is a four, participant four is a six, and participant five is a seven. Okay. And then we have a whole nother group of people. Hopefully, we randomly assigned people into these two groups. That's very important. But these are people who we have run and we measure their heart rate. And that would be person six got a seven, person seven got a five, participant eight got a three, participant nine got an eight, participant 10 got a nine. And so this is the way, so we have two separate groups of two separate people. And so what we have is what the heart rate of a group of people is without the exercise, and then a group of people after the exercise. Okay. And that is called a between participant design. Now, problems with it is the equivalence of the two groups. Let's imagine that you don't control this by randomizing people into the two groups. Let's say that you begin a study at 8 a.m. and the first 10 people that come into the experiment, you put them in the control group, and then the next 10 you put in the experiment group, just because it's easier to do it that way. I dealt with a student once who wanted to do this way, and she was not convinced of my telling her that that was the wrong way of doing it, but it is absolutely the wrong way of doing it. Because the problem is that maybe blood pressure differs in the morning and the afternoon. So it's not the exercise that's making the difference. It's that in the afternoon, people's blood pressure just tends to be higher. Throughout the course of the day, maybe blood pressure rises. So what you really want to do is to randomize. Every time someone comes in the laboratory, you flip a coin. If it's heads, they go in the control condition. If it's tails, they go in the experiment condition. And that's how you make groups equivalent. Now, there are many ways that you don't need to use a quarter. You can use a random number table. You can roll a die, and if it's an even number or an odd number, whatever it is that you use, but randomization is the key thing to make the two groups as equal as possible. Okay. Um, but how can you determine equivalence though? I mean, you might have some strange people in an experiment that just happen to be put into, especially when you have small samples. When you have 100 people, every one person's um, results won't influence the conclusions of the study all that much. But let's say if you only have 10 people in one condition and 10 in the other, one outlier, one person who's extreme might really bias the results of your study. And it's also difficult when there are confounding variables, where the example would be time of day. But any kind of confounding variable, such as culture, let's imagine that you have two groups, and in one group you have, seven Americans, three Japanese, and the other group you have, you know, seven Americans and three Japanese. In that case, you're going to have compositions of the group that are different. So it's not just that you have the treatment that differs between the two groups. You also have the composition of the group, and that can happen just randomly. Again, the more people that you test, the better, because the less likely that's going to happen. Now, most experiments use what we call a mixture within and between participant factors. Okay, so you might do something like study gender as your between subject factor. That's something that you can't randomize. Okay, but you might use whether or not they were at rest or exercising as the within subject measure. Okay, or you could assign people to one of two conditions: one where they take a drug that is supposed to help with your blood pressure, and then the other get the placebo. And then you could have male and female. Okay, so you could subdivide your between subject, and then you could have as a within subject design the heart rate at rest and heart rate after exercise. You can have as many factors really as you want, although there's limitations with that as well, but we'll get into that in a minute. But the problem is with mixed designs, they have a number of advantages, but they also have all the disadvantages of both within and between participant designs because they have features of both. So with the good, you get the bad, and that's always the issue when you're using sort of a mixed design. So most often threat to validity really is the presence of confounding variables. Okay, these are things that vary with the independent variable but influence the dependent variable. So for instance, you might be interested, as I am, in people's environmental attitudes on their behaviors. But environmental attitudes correlate with things like education. The more education you have, the more likely you are to have been exposed to the ideas of the threat that humans pose to their natural environment. And so you might be more concerned about CO2 emissions and things like that. So education and attitudes about the environment could be correlated. So the question is it the attitudes about the environment, or is it education that's influencing the dependent variable the most, right? Um, and so how do you deal with this problem? Well, what you need to do is to control for the confounding variable. Okay, so control really refers to the idea of the means that you use to rule out threats to validity. It could be experimental, it could be logical or statistical in nature. So in experiments that involve random assignments, we control things usually by using an experimental group and a control group. So the experimental group receives a treatment and the control group does not. So back when COVID was going on and the vaccine was being developed, they had groups of people, one of whom would take a shot that only had saline solution, so just nothing in it. And then the other had the shot that had saline solution plus the mRNA vaccine. And the question was, is that do people that got the shot with the mRNA vaccine, did they get sick, relative to the people that just got the saline solution that doesn't treat anything? And it turns out that those that got the COVID shot didn't get sick, and those that got the saline shot did get sick. Okay. And so what's the only difference between those two groups? And this was like 14,000 people. Okay, like 7,000 in one group and 7,000 in another group. So this is not like dealing with 10 people. So, what other than the shot containing the mRNA vaccine differed between those two groups of 7,000 people each? Nothing really, probably. Now, again, you could do a bad experiment where, let's say that you decided to do like what my student at one point was suggesting that I mentioned earlier, where you would just give people who came in the morning the COVID shot and people that came in the afternoon the saline shot. Well, maybe there's other differences between people that are morning people and afternoon people that might explain, the degree to which they were likely to get diseases. Maybe people that come in the morning to experiments, they tend to be more introverted, so they don't hang out with many people, so they're not exposed to a disease. Whereas people that come in the afternoon, maybe they're people that are into nightlife, for instance, and maybe they interact with more people on a daily basis, and that could explain why they're getting sick and the ones in the morning are not getting sick. So you want to exert control over your experiment to prevent those kinds of problems from occurring. So just imagine I'm doing a study where I'm interested in the effect of knowing a student's names upon grading across the semester. Okay. So I could divide the class in half. Half that I know what the name of the students are on their papers, and half I use a different random number each time for the 10 essays. So I don't know what the name of the student is. So one is the experimental group, the one where I know their name, and one is the control, the one where I only get the numbers. And I might track your scores across the semester, and at the end, explore whether the relationship between scores on the 10 essays where I knew the name are stronger or weaker than where I had only the random numbers. Okay, so I want you to think about what could be some potential problems with this design. I'll let you do that on your own. And experimental control really is only feasible in situations where you can randomly assign participants to different conditions, which you don't have in quasi-experimental designs. Okay, so imagine that you're studying cancer rates between flight attendants or ground crew. You can't randomly assign person to those tasks because they require training, right? They require expertise. And so maybe people that become flight attendants are different in other ways than people that work on the ground crew. Okay? Let's say that you're doing a study on gender. You can't randomly assign people to be male or female. And maybe there's something other than being male or female that, it could be something biological, it could be height. Maybe males have better spatial abilities, and which is what is a claim in the literature, because they're taller than females, so they're able to see beyond or further than what females are able to see because of the 3-inch difference in average height. You can't assign people to be alcoholics or not. I can't just get a group of people randomly to, put them into two groups and tell one group that you're not allowed to drink alcohol and the other group, pour alcohol down their throats until the point that they become, alcoholic because that would be unethical. And, you know, uh, alcoholism is related to genetics and other factors that you can't control that occurs over the course of someone's lifetime. Or attractiveness. You can't assign people to be attractive or not. I mean, you can manipulate this. I mean, there's been sort of experiments done where you have someone who dresses really nicely and wears makeup and, does their hair versus shows up in, looking terribly. and see whether or not that affects other people's behavior or their own behavior. But, you can't control everything. And so people will come into your laboratory and have characteristics that correlate with other characteristics outside of the laboratory that might influence how people react to them. So that's always a problem. So, random assignment, all participants have an equal chance of being in the control group or the experiment group. And again, there's many ways you can do this. You can flip a coin, you can use a random number table, which is in the back of most statistics textbooks. You can search for one on the internet, or you can use Microsoft Excel or Google Sheets and type this formula in equals rand and then two parentheses. That's not a zero, that's a left and then right parentheses, then sort by column. And that gives you a list of random numbers. Now, pseudo-randomization is often okay. In my experiments, what I do is that every other person that comes into my study is in one or the other condition. Let's say there's two conditions in the experiment. I pseudo-randomize it so that it goes, if your subject number is even, you get into condition one. If it's odd, you get into condition two. That usually works for most people and in most conditions, and so that's an okay way of doing this. Um, I'm just going to stop here for a second. Okay, so matching is another kind of experimental control. So rather than randomization, what you do is you make the control and experimental group as equal as possible by matching subjects both on a variety of factors. So you could make sure that your control and your experimental group have people the same age composition, the same gender, the same major, socioeconomic status, ethnicity, whatever it is. And so what you do is you get a huge sample of people and you randomly choose two people of the same age and you randomly put one of them in condition A and then the other one in condition B. And you do that for all of these things so that these two groups are matched in terms of a particular feature. And that's one thing that you can do. It's somewhat common, but you should only match when you suspect that the variable in which you match might influence a dependent variable, not if you just don't know. And it also must be feasible only when you can determine a matching variable that it has an influence on the experiment. So if you don't know um, that blood type might have an influence, you might not even know to measure blood type and use it as a matching factor. So that's another problem with matching. You can also include what are called nuisance variables. Some things you can't match or randomize, but you might not even have a hypothesis as to whether it would influence the dependent variable. Let's say the place that you're from, if you're from Pennsylvania or you're from New Jersey, you might be able to, you know, include it as a factor in your experiment, but it's called a nuisance variable that you're exploring whether that factor has a significant effect using one of these statistical tools. But it's not the same thing as a confounding variable because nuisance variables really is a second independent variable, whereas a confounded variable is one that varies with the independent variable. So a nuisance variable is just a variable that you know every subject, what state they're from, and you include it in not having any idea whether or not it's going to affect the dependent variable. If it does, then maybe that's a reason to do another study. Maybe people from Pennsylvania are very different from people in New Jersey. Certainly, the highways in New Jersey, as a person from Pennsylvania, I live in Philadelphia. I can never drive in New Jersey. I have no idea how the roads work. And so for me, it's, Route 130 could be Mars as much as I know. You know, uh, but that's just me. I mean, and for some of you, maybe driving in South Philadelphia might be like driving on Jupiter or something. And then there's something called statistical control, where you can use complex statistics, such as in correlational analysis, something called partial correlation, in analysis of variance, something called ANCOVA. Um, in regression, you can use dummy variables. There are ways of dealing with, um, nuisance variables, confounds, by using advanced statistical techniques. But again, this is beyond what you can do in a course like this. So I just want to point that out. So control in the laboratory is achieved by treating all participants equally. So every subject should be have the instructions explained to them the same way. It shouldn't be that males get more attention or females get more attention than the males do. Everyone should be treated equally so that there's no potential influence of the actual experimenter. This is related to something in the past called the Hawthorne effect, where, people behave differently when they know they're being watched. But, if you let subjects know that they are being watched very carefully, that could really influence the results. So you need to, kind of do a good job of this. All participants being tested on the same equipment by the same experimenter using the same instructions at the same time of day. It's not always possible to do all of that. Sometimes I have multiple research assistants doing my data collection, but even then, there are some effects that might not be controlled for. The attractiveness or the niceness of the experimenter can have differential effects on participants. As I mentioned earlier, I had once had a really mean research assistant who treated some subjects really nasty. And if you're treated poorly when you come into the laboratory, you're not going to give great data, because you're going to be resenting that you're there. The gender of the experimenter also has effects on developmental studies. I found with doing work with children that, at least 20 years ago when I was doing that work, that female research assistants just had much more success with children. Maybe it's because children spend more time with female caregivers, whether it be the female in a nuclear family, the female parent, or at school, there are more female, preschool teachers, things like that. So, again, there are things that, might not be able to be controlled. I wasn't about to dress up like a woman and pretend to be a woman just so that children would, perform better in my experiments. But also some effects can't be controlled in the lab. So, I can't control whether you're Japanese or American or if you're, you know, uh, from a African American background or a Caucasian American background. Some things we just can't control because people bring them into the laboratory as features that they have. So, but just being very careful when you're in laboratory experiments that you're doing it in a way that will, not bias results in one direction or another is really important. Um, But you also have to worry, if it's a case that the laboratory settings or the experimenter makes a fundamental difference in your results, you have to wonder about both external validity and reliability. If your measures are so sensitive, what about how people would behave in other settings, other times? Would the results be the same? Or if someone tries to replicate your study at the next university down the road, at Rowan, for instance, or at Temple, will they come up with the same results? Um, so you really should avoid methods where the dependent variable is significantly influenced by such contextual factors, because it just suggests a very tenuous link between your independent variable and dependent variable, which is what we began with, internal validity. So choose your measures wisely, but also just be very careful in doing experiments. This is why not everyone is an experimental psychologist. It's not easy to do this kind of work. So of course, not all experiments can be done in a laboratory. Okay. You might be interested in real world behaviors, whether the amount of clothes that one wears determines the number of sexual advances at a frat party, whether a smiley face results in a larger tip, or whether looking at smoking behavior at bars, although, at least in New Jersey and Pennsylvania, there really isn't all that much smoking in bars anymore. Although it's certainly not in New Jersey, but in Pennsylvania, once you get out of some major cities, well, even in major cities, people still do smoke at bars. Um, in such observational methodologies, you should try as best to achieve randomization. You know, um, randomly choosing which people at a frat party to study, randomly giving people a smiley face or not, or randomly choosing 10 bars from the Cherry Hill phone book. But often randomization is not always possible, so you have to deal with that aspect of the situation. Um, so use objective rather than subjective measures. So um, an objective measure is something which is really easy to observe. Subjective is more sort of one's own opinion. So the number of times a person is approached at a frat party, as opposed to asking other frat party goers to rate the likelihood of approaching a person, or the percentage tip versus a subjective rating of how friendly a patron was, or the number of cigarettes a person smoked per hour, rather than how much the person seems to enjoy smoking. Also, it's good to have inter-rater reliability. This is where you have multiple people code behavior to the degree to which they agree. So when you have high agreement, you can be confident of your measure, but low agreement, you can think that it's too subjective. You know, if you were doing a study where you're seeing if men or women are more likely to blow through red lights, it would be good to have a second person there with you who's doing the same study and to see at the end of the study, at the end of that hour, that both of you have the same data. If you don't, then maybe you're not really good at being able to judge what blowing through a stop sign is or whether or not the person in the car is a male or a female. Both are possible outcomes. Um, but replication is always key. Conduct the study multiple times, not just at the intersection down the street, but the one across town, another one in a different city, in multiple contexts to see if the result is consistent. And I'll end with this, is that, the elegant experiment is one where you use the simplest possible method to explain the most complicated phenomena. I've often said jokingly in class that like a great experiment's sexy in the sense that it's elegant, it's gorgeous, and there's sometimes when you read an experiment, you're like, damn, why didn't I not think of that? But in a general sense, even complicated experiments can be beautiful as well. But always remember that the simplest answer is preferred over the most complex in most cases. And always creativity and simplicity is a key to good research design. And so that's going to be how I'm going to end. You'll be criticizing some inelegant designs in your homework, but I'm going to end here. And I hope that you found control and threats to experimental validity to be a useful tool for being able to read future studies.